Hello everyone, welcome to another session of KSS, Kindle Science Station. Let us today analyze the fascinating science behind the world of colors and how colors are decoded. In this part 1 of the video, we will explore the theory behind the color codes. And in part 2, we will do some experiments with spinning discs to see the mixing of colors. So let's start first with the theory part. We are all used to seeing different colors and identifying them with their names. But how do we decode these colors? Actually, it depends on both physics behind it and how our eyes perceive them. That is, there is also a biology involved in it. Let us understand what happens when white light falls on 4 different objects: pure blue, pure red, pure white, and black. So, if we see blue color, it means that the particular objects can absorb all other colors of light except blue, and only wavelength corresponding to blue color reaches our eye. Therefore, when light enters the human eye after reflecting off a surface like piece of a paper or a palette of paints, the color we see depends on which wavelengths of lights are absorbed by the surface and which wavelengths are reflected by the surface into our eye. So in this example, we are able to see the surface blue because the wavelength of blue reached our eye. Similarly, when we see a red surface, it means that the light of wavelength corresponding to red reached our eye. In case of a white object, all wavelengths of light are reflected by the surface and the surface appears white to our eye. When object is dark or black, all wavelengths of light are absorbed by the surface and no light reaches our eye and the surface appears black to our eye. I am sure we all learned this model at school that there are 3 primary colors: red, yellow and blue. This old RYB color model we all used as kids when we mixed paints and colors while doing drawings. When we mixed yellow and blue, we got green color. When we mixed yellow and red, we got orange color. And when we mixed blue and red, we got purple. And these derived colors, we called them as secondary colors. This RYB model became the foundation of color theories in 18th and early 19th centuries, where artists mixed paint pigments to produce different colors. RYB color model is subtractive system. We will learn more about it. A mixture of all these 3 primary color results into darker approximation of black, though actually it results into muddy brown color. When we mix paints, dyes and pigments, it results in an absorption or subtraction of certain wavelengths from the white light. So this absorption or subtraction is creating a new color by removal of certain wavelengths from the light. Hence, it is called a subtractive system. Like in case of a yellow paper, all wavelengths except yellow will be absorbed by this paper and only yellow wavelength will reach our eye. So the paper appears yellow to us. In the late 19th century, German and English scientists established that a color model based on red, green and blue was a better for describing human color perception because the cones in human retina responded better to these colors of light. In addition to providing a good description of human color perception, the RGB model today is the basis for displaying colors in television, computers and mobile screens. This RGB model is also used for recording colors in digital cameras, including still image and video cameras. The RGB model is an additive system. So why RGB color model is additive system? Let us understand this. Suppose we want to view a yellow screen, then as per this RGB color system, it will emit green and red light to create the illusion of a yellow light. As all the wavelengths created reaches our eye, it is an additive system. In this example, it is important to realize that the computer isn't creating a yellow light. The computer is just creating an illusion of yellow light by mixing red and green, which is good enough to trick the human eye. As the human eye cannot distinguish between the natural yellow light and mixing of green and red light from the computer. It is also important to note that additive colors begin as black, as the screen of TV, computer, mobile is black when no light is present, and become white as more red, blue, or green light is added. So, when we compare the additive versus subtractive system, we notice that in our examples, both the screen and the paper appeared yellow to us, but it had a different theories behind it. If you are getting confused, the easy way to remember the difference between additive and subtractive color mixing is that the additive color mixing is what happens when we mix lights of different colors, whereas subtractive color mixing occurs when we mix paints, printer ink, or other physical colored material. Another color model prominent today is CMYK color model. It stands for cyan, magenta, yellow, and key black colors. This is the modern subtractive process model. This is printer's favorite color model. Secondary colors are made of red, green, and blue. Different mixtures and intensities of four colors could produce just about any color one needed for design printing with powerful effect. Today, CMYK remains an industry print color standard. Note, the design files which we see in the computer are in RGB format, which has to be converted to CMYK format for printing. The Adobe company released the coding of this conversion, which is widely used today in all printings. Here, all three color models are compared into a tabular form for your quick view. Hope now you understand the RYB was an old model which was the painter's favorite. The RGB model is what is used in the digital displays of all our electronic devices, and CMYK model is the printer's favorite model. In part 2 of this topic, I will come with actual experiments on various combination of color mix tried on spinning discs. So keep tuned to KSS Kindle Science Station. Bye bye for now.